In this question, we are being asked to find the wavelength of a wave, and we're going to use the wave equation. So we're going to use the wave speed divided by the frequency gives us the wavelength. At present, we've got neither the wave speed nor the frequency, so we have to derive those from the information that we have got. So we're going to find the wave speed by doing the distance that the wave travels divided by the time taken for it to travel that distance. So our distance here is 45 meters, and the time that it takes is 25 seconds. So we do 45 divided by 25, and we're going to put that into our wave equation in just a moment, so we'll leave it at that. Meanwhile, we need to find the frequency, which we can find by doing 1 divided by the time period. Time period, we're told in the question, is 2 seconds. So that gives us a frequency of half a hertz. Putting those numbers into our wave equation now. And when you're doing your PAT test, it's always important to try and do as many of these calculations in your head to speed things up a little bit. So what I decided to do here is I'm not very good at dividing by 25. So what I did, I multiplied both the top and the bottom by 4 to make it 100 at the bottom, because 100 is a little bit more easy to divide by. So we have 360 divided by 100, and that gives us 3.6, which is answer C. Now this question looks really unfamiliar, but it's actually quite straightforward, because we're told what the equation that we need to use is. So it's this equation that involves alpha and T, which Ts, which is the surrounding temperature, take away the temperature that we want to cool the food to. The only complication is the efficiency of the refrigerator is 30%. So just plugging those numbers into this equation that we've been given here. So alpha, we're told, is 15, and our temperature of the surroundings is 26 degrees Celsius, and the temperature that we want to get our food to is 6 degrees Celsius. Plugging those numbers in, we find that we need a power of 300 watts. But we're told that the efficiency of the refrigerator is 30%, so we just need to divide by 0.3, and so 300 divided by 0.3 is 1,000, so 1,000 is 1 kilowatt, so it's answer A. So it's a reasonably straightforward question that relies on us knowing about the phases of the moon. So I'm just going to make a quick sketch of what we need to, how we can kind of visualize this question. So we've got our diagram of the sun there, and we've got the Earth there. Just to emphasize, this isn't to scale both the diameter of the planets or the distance between them. So it's just to kind of help us visualize. And there's the moon there. Now this is the sort of setup that we have for a lunar eclipse, where the Sun, Earth and Moon are in syzygy, and if we just colour in that side of the moon there, so to represent that that side is in shadow, then if we were looking at the moon there, then we would see the full moon. So that would be answer B, the full moon. So this question is about the distances to stars and the power that they radiate. So I'm just going to draw a quick diagram to help us visualize this. So we've got our Earth there, and we've got our nearest star, which is 10 light years away, and we've got the more distant star that we're talking about in this question, and that is 20 light years away. And the thing that we need to know about the brightness and distance is that there is an inverse square law. So we're going to use B to represent the brightness, and B is proportional to 1 over the distance squared. So we need to find the ratio of the distance to the more distant star squared to the the closest star squared. So the more distant star is 20 light years away. So we're going to do 20 squared divided by 10 squared, which gives us 400 divided by 100, which gives us a ratio of 4. So that's answer D. So another astronomy question here, and for this one we need to use Kepler's third law of planetary motion, which is that the time period squared is proportional to the distance from the Sun cubed. So that means that the distance to the Sun cubed divided by the time period squared gives us a constant. And that will be the same constant for all the different planets that we're looking at in this question. So we've got the nearby planet, which is 0.4 astronomical units away. So we're going to do 0.4 cubed, and we're going to divide that by the time period squared. So it's 3 days squared. We don't need to change any of the units here to meters or seconds because we're using the same units in both examples. So the more distant planet has a time period of 24 days. So when we put those numbers into our equation, then here we've got this is equal to a constant, and this is going to be equal to the same constant, so that's how we can equate them in this equation. So you should be able to do these calculations in your head or on scrap paper while you're doing your PAT test, just to so they're not too complicated. It's just a matter of just some long multiplication there. So that's what we're doing here, just plugging those numbers in there. And what might be a little bit trickier is just finding that cube root. So once we plug all the numbers in, then what we've got is this cube root of this number that includes some decimals. So the way that you could go about trying to work out what the cube root of that is to say that, well, 1 cubed is equal to 1 and 2 cubed is equal to 8. So they're the sort of common cube numbers that we should know. And 4.096 is somewhere in between those. So immediately we can rule out answer D and answer C because neither of those are between 1 and 8. So 16 is obviously higher than 8, and 1 is, it's obviously the same as 1. So we've got two possible answers. It's either A, 1.6 astronomical units, or B, 3.2 astronomical units. If we do 1.6 cubed, then we do get 4.096. And if we do 3.2 cubed, then we get 32.768. So that's clearly wrong, and 1.6 cubed is the right one. So answer A is what we're looking for there. So in this question, you need to utilise the rules for finding the total resistance in networks, and we're going to break this problem down into 3 parts. Initially, I'm going to find the total resistance of just those 2 resistors that I've circled there, which can be 1 over the total resistance is 1 over one resistance plus 1 over the other resistance. Both resistors are R. So if we add those together, then we've got 2 over R, so our total resistance is R over 2 there. Next up, we're going to find the total resistance of the part that I've circled in blue there. So to do this, we just add together the resistances. So we found out that R over 2 is the resistance of those 2 resistors in parallel, and we add that total resistance to the one that's in series to those. And just to make adding those fractions a little bit easier, times both sides by both top and the bottom of the fraction there by 2. So you add them together. So the bit in blue has a total resistance of 3R over 2. Now we're going to take that 3R over 2 and then say that that's now in parallel with that one resistor all by itself at the top there. Again, we use the resistors in parallel equation. 1 over the total resistance is equal to 1 over the first resistance. So 1 over we found the first resistance with 3R over 2, so 1 over 3R over 2 is 2 over 3R. Then we add that to our 1 over R, which is our resistor by itself. So we leave the 2 over 3R by itself, and then we times both the top and the bottom side bit of the fraction there by 3 to make adding those fractions possible. And then we find the total resistance by finding the reciprocal of that. So 3R over 5 is our final answer there. So it's answer D we're looking for. This is a fairly straightforward question about a transformer, and to answer this one we need to know that the ratio of the number of coils on the primary, so it's NP, to the voltage on the primary, VP, is the same as the ratio of the number of coils on the secondary and to the voltage on the secondary coil. So once we know that, we can just start plugging our numbers in. So the number of coils on the primary, we are told, is 50 turns, and the voltage on the primary coil is 240 volts. And we are told that the voltage on the secondary coil is 120 volts there. We're told that it draws a current of 1 amp, but we don't need to use that bit of information. So it's just extra little bit of information that we don't really need to use. Rearranging for NS, the number of coils on the secondary coil, and putting our numbers in, we can simplify it down, and what we end up with is 25 coils on the secondary, which is answer C. In this question we've got an electric motor and it's lifting up a mass of 100 grams, and we're being asked how quickly the electric motor lifts it up. Now to answer this we need to use the fact that power equals voltage times the current. So our voltage is 6 volts and our current is 1 amp. So 6 times 1 is 6. And what we've just found there is the number of joules per second. So 6 watts means 6 joules per second. And that's what we're going to need to know, because we're going to equate that to the work done in lifting up this mass. So the work done is the force times the distance. Our force in this case is 1 Newton, because we've got 100 gram mass, 0.1 kilograms. So 0.1 times acceleration due to gravity, which in this particular paper, so when you're doing your PAT tests, is 10. So it's 0.1 times 10, which is 1 Newton. So our work done, what we're going to do is find our work done divided by time, so we can then equate it to the power. So work done divided by time is power. So we're going to divide both sides of that work done equation by the time there. And what we have then is the work done divided by time is the power, and we got the force times the distance divided by the time, and distance divided by the time is the speed, and that's what we need to find out. So we need to rearrange it so that we have the speed there. So we just do the power divided by the force, tells us the speed. So our power was 6 and our force was 1, so 6 divided by 1 is 6. So it gives us a speed of 6 meters per second. So it's answer B that we're looking for there. So this is a reasonably straightforward question about vectors, and so we've got a object, so it's a toy car. I'm just going to use a box to represent that, and it's got a downwards acceleration of 10 meters per second squared. So we don't need to worry about using the mass at all because the acceleration is independent of the mass, and we want to find the acceleration down the slope. What we know about this is we know the angle of the slope, and the angle of the slope is 30 degrees to horizontal. So that must mean that this angle here is 60 degrees. So we're going across the angle, so we need to find the cosine of the angle. So the cosine of 60 to resolve this vector. So it's going to be the acceleration due to gravity, which is 10 meters per second, times cos of 60. Now we should know that cos 60 is equal to a half. So there's 0.5. So the acceleration down the slope is half of 10, which is 5 meters per second squared. So it's answer D we're looking for. So another question about vectors here, and we've got a boat that's crossing a river. So we're just sketching our river here. And we're told that the river is 100 meters wide, and the river flows from east to west at a rate of 5 meters per second. So I'm just labeling that 100 meters wide there. We don't actually need to use that information, but we'll just pop it in there anyway. And there's our river flowing from east to west at a rate of 5 meters per second. Now we need to get from this point that I've just marked on the one side of the bank to the opposite point, and we're going directly across the river. Now to do that we're going to need to take a course kind of similar to the arrow that I've just drawn there. And the boat can travel at a maximum speed of 10 meters per second. And we need to know at what angle does the boat need to travel. So we're going to just construct a vector triangle here, and the top part of the triangle represents the flow of the river. That diagonal part of the triangle represents the speed of the boat, and we're looking for the angle that I've just marked there, theta. So we need to find the sine of the angle because we've got the opposite and the hypotenuse, and so we need to do the opposite divided by the hypotenuse. So that's 5 divided by 10, and 5 divided by 10 is a half, and we should know that sine, so inverse sine of a half is 30 degrees. Now there's two answers that involve 30 degrees, that's A and C, but we need to rule out which one it is, and if we label that as north, then our angle is towards the east, which I'll just label there. So our answer is 30 degrees east. So first of our written answers now, and it's got 3 parts to it. So we're just going to have a look at part 1, where we're trying to find the velocity that the ball is launched horizontally. Now we've got this catapult, so I'm just going to draw a quick picture of how I visualised it. So there's the spring, and there's the massless cup, and there's the mass sitting in the massless cup, and it has initially a length of length L. And then the catapult is extended backwards, and it's extended backwards. There's the massless cup again, and it's been extended to a length of x. So the amount by which it's extended is x minus L. So I just made our diagram a little bit smaller, just moved it to the side there. And to answer this question, to find the velocity, we're going to find the elastic potential energy that is stored in this spring, and we're going to equate it to the kinetic energy, and then find the velocity that way. So the elastic potential energy is given by half k delta x squared. And it's important to note that when I'm using delta x here, I'm not talking about the x of our diagram. I'm just talking about how you might read it in a textbook. But our delta x in this case is x minus L. So our elastic potential energy is half k x minus L squared, and we've equated it to the kinetic energy half mv squared. So we've just cancelled the half there to give us k x minus L squared equals mv squared. And now we just need to solve it for v. So we're going to divide both sides by the m there to give k over m x minus L squared. And that's equal to the velocity squared, so we just need to square root both sides. And that gives our velocity equal to the square root of k over m x minus L. Second part of the question involves us finding the vertical velocity of the catapult. So I've just turned our diagram to the side there, and again we're going to do it using the elastic potential energy, and we're going to equate it to the kinetic energy. But this time there's the added complication of there being the catapult needing to do some work against gravity to lift it back up to that equilibrium position. So some of the force, so I'm just labelling it there. So that is the gravitational potential energy. That's the work done against gravity in lifting it back up to that equilibrium position. So the elastic potential energy that's stored minus that little bit of work done, minus that gravitational potential energy, will give us the kinetic energy. So this one's a little bit more involved because it does involve this added complication of that gravitational potential energy. So our elastic potential energy is just as before, is a half k x minus L squared. And our gravitational potential energy is going to be the mass times acceleration due to gravity times the height that it's lifted through. And later on I'll substitute the height for x minus L. And our kinetic energy there is half mv squared. So first step that we're going to do, we're trying to find the vertical velocity. So we're going to divide both sides by a half and divide both sides by m. So that gives us k over m x minus L squared minus 2gh. And that's going to be equal to the velocity squared. So we need to find the square root of that. So it's the square root of k over m x minus L squared minus 2gh. And that gives us our velocity. And at this point I'm just going to rewrite it just by substituting the h for x minus L, because that distance h in this case is x minus L. So final answer for velocity is the square root of k over m x minus L all squared minus 2g x minus L. In the last part of this question we need to find the height that the ball reaches when it's fired vertically, and to do that we're going to use the kinetic energy that the ball has when it leaves this massless cup, and we're going to equate that to the gravitational potential energy. So our kinetic energy half mv squared is going to equal the mass times acceleration due to gravity times the height. So the height is what we're looking for. And if we rearrange this, the m's cancel, so we end up with the height is equal to the velocity squared over 2 times acceleration due to gravity. So if we use the value for, or the expression we had for v squared from last question, then what we have is k over m x minus l squared minus 2g x minus l, but we've also got that 2g, so let's put that at the bottom of the fraction as well. And what we can do is just rewrite this, cancel in those 2g's in that second term there to give us k over 2mg x minus l squared. The 2g has been cancelled, leaving just x minus l there. So in this question, we've got a electron that's being accelerated through a potential difference. So it's being accelerated from the negative to the positive there. So I just labelled that as an E just to represent the electron there. And this bit in blue represents perhaps a positive and negative plate. It says that it's travelling through an electric field. So that electric field is going to cause an upward force on the electron as it's passing through there. Now it's also going to have a downward force, so we can use Fleming's left-hand rule to work out which way the downward force is going to be. So our current finger needs to be pointing in the direction that I've labelled I. Our thumb needs to be pointing downwards, so that gives us our field pointing towards us. So the field coming out of the plane of the screen there, and that provides the downward force. And we need to find the voltage that will accelerate the electron such that those forces will cancel out. So the force of the electric field is little e times big E, and the force from the magnetic field is EVB. So we need to find we need to find the velocity when those forces are the same. So I've equated them there, cancelled out the electron there, the charge on the electron. So the velocity that it needs to be going at for those to cancel out is E over B. E, we are told, is 1,000 volts per meter, and B, we are told, is 1 times 10 to the negative 5 teslas. And putting those numbers in, then we get 10 to the power of 8. So having found that velocity being 10 to the power of 8, we need to know what voltage will cause the electron to accelerate to such a speed. Now we can do that by finding out the work done on a charge is the voltage times the charge, and we're going to equate that to kinetic energy to find that voltage, because we're told the mass of the electron in our question here. So if we equate those two, then we get half mv squared equals the voltage times the charge. So we've got half times by the mass of the electron, which is approximately 10 to the negative 30. And the velocity we found a moment ago was 10 to the 8 meters per second. So we'll take that velocity, square it. And what we're doing here, we're taking the charge there. So charge on the electron is 6 times 10 to the negative 19 coulombs. And we're trying to look for V, that voltage. So having done all that, then a lot of this you can do in your head. So for example, this section here, you can just use the laws of indexes there. So that's how I've arrived at 10 to the negative 14 there. I've brought the half, so I've divided both sides by half to cancel that out, to give 32 times 10 to the negative 19 times our voltage there. And now we're just going to solve it for the voltage. So our voltage that we need to get our electron to a velocity of 10 to the 8, such that it will cancel out those two competing forces, is 1 over 32 times 10 to the negative 5 volts. Okay, so this question is about a radioactive source that's emitting alpha, beta and gamma radiation. So we need to know the properties of alpha, beta and gamma. Now we're given some different statements here. So I'm going to call the first statement statement A, and that is that the sheet of aluminium of 1 centimeter thickness. Now we should know that beta particles are stopped by 1 centimeter of aluminium. So it goes down from 100 counts per minute to 100 counts per second to 50 counts per second. So that means that it's gone down by 50 there. So our beta particles contribute to 50 there because they're stopped by the aluminium. Statement B says that when it's taken completely away, radiation level is seen to fall to 10 counts per second. So 10 counts per second there is the background radiation. So 10 counts per second is the background radiation there. Therefore, that must mean that the gamma radiation is 40 because 50 plus 10 plus 40 is 100. Now we haven't come into the realms of the alpha particles yet because it was placed at a distance of 10 centimeters, and alpha particles are stopped by a couple of centimeters of air. But when it's taken to 1 centimeter, then the count, that's when the alpha particles start getting detected, when it's really, really close up to the detector there. So the alpha particles, they contribute 300 counts per second to our source. So our ratio of alpha, beta to gamma, well, our alpha contributes 300, our beta contributes 50, and our gamma contributes 40. So we can simplify that ratio to 30 to 5 to 4. First thing to note about this question is this sentence here has got a typo. So here where it says smaller, it should say larger. So it says that the base area, i.e. the width times the length of the large box, is 10 times, originally it says 10 times smaller than the base of the small box, but it should be 10 times larger. So that's a typo, and it's acknowledged by the exam board that set the exam. So what we're going to do is we've been given 5 statements, A to E, and we're just going to go through each statement kind of working out what it means. So statement 1 is that 8 small boxes fit inside one medium box. So 8 small boxes fit neatly inside one medium box. So that means that the volume, this is the volume here. So the width times the length times the height. So 8 of those of the small ones go into one of the medium ones. We're also told that the length of the small box is the same as the height of the medium box. So length of the small box is the same as the height of the medium box. We are told that the base area, the width times the length of the large box, is 9 times that of the base area of the small box. So this is the base area of the small box, this is the base area of the large box, and we need 9 of those, 9 small box areas to fit in one large box area. We are told that the lengths of all 3 boxes add up to 2.4 meters. So the length of the small box plus the length of the medium box plus the length of the large box equal 2.4 meters. Final thing that we're told about this is the width of the medium box is twice the height of the small box. So there we go, the height of the small box, so twice the height of the small box, is equal to the width of the medium box. And each of these facts, so I've just hidden the facts up there, and what we're looking for is the lengths of the three boxes, and the width to height ratio, and the width to length ratio. Now, to do this, we're going to need to make a substitution. So I'm going to call x h over w, so the height divided by the width, and I'm going to call y I'm going to call it the length divided by the width. And we can do that because each of the different boxes got the same width to length ratio and the same height to length ratio. So I've just put those up there as well because that's a fact that I'm going to use throughout this solution. So we can say, because I've made x the height divided by the width, it's the same true for all boxes. So the height of the small box there divided by the width of the small box, we're going to call x. So if we rearrange that for the height of the small box, then we've got x times the width of the small box. I've called y the length divided by the width. So the length of the small box divided by the width of the small box is going to be y. So the length of the small box is y times the width of the small box. Now I'm going to substitute these numbers in, so these kind of substitutions in to the relationship A. So I'm going to use this, and I'm going to put these instead of the height of the small box, I'm going to use x times the width of the small box. So we're told that the 8 small boxes fit in the medium box. So we're going to have the width of the small box times the length of the small box, which I have just made y times the width of the small box. And then that's times by the height of the small box, which I've made x times the width of the small box. Now each of the small, medium and large boxes, they've all got the same kind of aspect ratio, if you will. So we can make just the same substitution for the medium boxes as well. So what I'm trying to do here is get rid of some of these variables. So I've gone from having 6 variables originally in A, and then I've whittled it down to 2 by making that substitution. The x's and the y's end up cancelling. So what we end up with is 8 times the width of the small box cubed is equal to the width of the medium box cubed. If we take cube roots of both sides, then cube root of 8 is 2. So what we find that the width of the small box is 2 times the width of the medium box. And because we've done that, we can also say that the width of the height of the small box is 2 times the height of the medium box, because they share that kind of aspect ratio as I just mentioned, and the length of the small box is 2 times the length of the medium box. So I'm going to take those facts and I've put those up there because we're going to need to know them later. So next thing that I'm going to do is I'm going to use statement C to help us again get rid of some of those variables. So here we've got an equation that's got 4 variables in. Just pop that to the side there, make a little bit of space just on the left here, and this time I'm going to make the y equal to the length divided by the width. So the length of the small box divided by the width of the small box, and rearrange that to get, so y times the width of the small box is the length of the small box. Also going to make y the length of the large box, divided by the width of the large box. And again, rearrange that for the length of the large box. And what I can do is I can take this bit here and this bit here, and I can put them in this equation here. And in doing so, we can cancel out some of those variables. So on one side of the equation, I've just got those W, the width of the small box, and I've got Y here, but that's a constant, and we'll see that cancels. And over here, I've got just the width of the large box there. So there we go, our Y's cancel. And what we end up with is 9 times the width of the small box squared. And that's equal to the width of the large box squared. Taking square roots of both sides, we find that the large box is 3 times as wide as the small box. And because they share that aspect ratio, the height of the small box is 3 times smaller than the large box, or the large box is 3 times bigger, and the large box is 3 times longer as well. So again, I'm going to put those facts up there just so that we can use them later. So I'm now going to start looking for the lengths of the different boxes. Now statement D tells us that the length of the small box plus the length of the medium box plus the length of the large box is 2.4 meters. But instead of using the length of the medium box, I'm just going to use the fact that we know that the medium box is twice that of the small box and the large box is 3 times that of the small box. Now we've got an equation where we've only got one variable, so it's quite straightforward to solve for the length of the small box, to find that the length of the small box is 0.4 meters. So I'm just going to write that on the side there, because that's one of the important bits of information that we needed to find out. That's one of the goals of this particular question. Now we're going to use statement D to find the length of the medium box. Now the length of the small box is half that of the medium box. And the length of the large box is 1.5 times the length of the medium box. We can find that out from the facts that we learned about earlier. So these facts here can tell us that. So we've got an equation now with just the length of the medium box, and we can solve that for the length of the medium box to give the length of the medium box as 0.8 meters. So again, I'm going to write that important information down on the side there. Now we're again going to use statement D. Now that we've got the length of the small box and the length of the medium box, we know the length of the boxes in total, so we can just simply find the length of the large box by just using a simple equation like that. To find the length of the large box is 1.2 meters. Now we're going to use statement E to find the ratio of width to height and width to length. Now statement E told us that the width of the medium box was twice that of the height of the small box, and we know that they're equal to other kind of facts about this question as well. So they are also equal to the width of the, so they're also twice the width of the small box. So we're looking for that width to height ratio. So we can use the width of the small box and the height of the small box there, and we find that they have got a ratio of 1. So width of the small box divided by the height of the small box is 1, and that's the same for all the boxes. Final thing that we need to do is find that width to length ratio. So we know that the length of the small box and the height of the is equal to the height of the medium box, and then they're both equal to 2 times the height of the small box. So what we've got is then we can say that the width of the small box is twice all these other things as well, and what we've got is the width of the small box and the length of the small box. So put those equal to each other, and we find that the ratio of the width of the small box So the length of the small box, which is what we were looking for, is a half. So just to summarise these points, we've got the width to height ratio here, the width to length ratio here, and the lengths of all the individual boxes. This long question is a mechanics question, so we're going to start off with finding the elastic potential energy of our drawn back bow and arrow, which is so elastic potential energy is the half times the force times the distance. So it's a half times our force, which is 120 newtons, times the distance that it's pulled back, 0.6 meters, and that gives us 36 joules of energy stored in this drawn back bow. And we're going to equate that to the kinetic energy, and that will tell us the speed of the arrow when it leaves the bowstring. So we're going to rearrange our equation for kinetic energy, half mv squared, to make v the subject. So that's the square root of 2 times the kinetic energy divided by the mass. So we've got 2 times 36 was our energy stored in the bow there, and mass of the arrow 20 grams, 0.02 kilograms, and number crunching that gives us 36,000, sorry, my bad, 3,600, and we need to find the square root of that, which is of course 60 meters per second. Now we're told in this question that some of the stored energy doesn't go into accelerating the arrow, but it accelerates the arms of the bow instead. So it's very tempting to just take this fraction that they've got here and just multiply that by the velocity, but we've got to make sure that it's not the velocity that's reduced by this, it's the energy that's reduced by this. So we're taking the 36 joules of energy that was stored before, and we're multiplying it by this factor, so it's 25 joules of energy left over, and that's the energy that goes into propelling the arrow forward. So we're just going to use the same equation that we used before, and the only difference is instead of 36 we're using 25, and when we put those numbers in we end up with the square root of 2,500. Square root of 2,500 is 50 meters per second. Now we're being asked how long in time it takes the arrow to reach the target that's 50 meters away. Very straightforward. We use the time is distance divided by the speed. We're told that the distance is 50 meters. We worked out what the speed was. That was 50 meters per second. So therefore the time that it takes is 1 second. So in this question we're being asked how far above the centre of the target they need to aim to ensure that it strikes the middle. So we need to take into account that the arrow will fall as it's moving through the air. Now this is a Suvat equation, so we're going to need to use the equations for constant acceleration. So easiest way to start that, SUVAT, we know that the time is 1 second, and we know acceleration due to gravity is 10 meters per second squared. Originally, so it's when it starts falling, it falls at, it's got a velocity of 0, so we can use S equals ut plus half at squared. Ut cancels out because u is 0, so half at squared. So we've got a half times the acceleration due to gravity, which is 10, times our time, which is 1 squared. So that means we have to aim 5 meters above the target. In this question we need to use the idea that the work done to slow the arrow down needs to be the same amount of work as the kinetic energy, so we're going to make the kinetic energy equal to the work done to slow it down. And kinetic energy is a half mv squared, and the work done is the force times the distance. But this is slightly more complicated than it looks because there's two components of the velocity because it's making a curved path like that. So there's going to be a horizontal and a vertical component. So there's your vertical component, which I'm going to call Vy, and there's a horizontal component as well, which I'm going to call Vx. And we need to find a resultant, which is that diagonal arrow that I've just drawn there. So to find Vy, so we're going to find Vy first. We're going to just use the fact that the arrow is going to be falling. So we're going to be using u plus at. So u is u is 0, and we're going to plus at, so acceleration due to gravity times the time that it's falling for, which is 1 second. So our vertical component is 10 meters per second. We worked out our horizontal component earlier on, which was 50 meters per second. Now we need to find the component of those two. So we need to use Pythagoras' theorem. So we do 10 squared plus 50 squared, and that will give us our resultant velocity squared, which is so v squared is 2,600. I'm going to leave it just as v squared for the moment because we're going to use it in our kinetic energy equation, which is half mv squared, so we're going to square it anyway. So we've got half times 0.02, which is the mass of the arrow, times v squared. So as I say, just leave v squared as it is there. And we're looking for the force, so we need to do force times the distance. So we've got the force times the distance there. Distance is 0.005 meters, so 5 millimeters, 0.005 meters. So our force, once we've done all that number crunching, is 5,200 newtons. In this question we need to find the velocity that the target moves backwards, and this is a conservation of momentum question. So m1 is the mass before, v1 is the velocity before, m2 is the mass after, and v2 is the velocity after. And our mass before is of course the mass of the arrow, so it's 0.02. Our velocity is the square root of 2,600, which we had in our last question. This is a so when the arrow strikes the target, it sticks in the target. So this is what we got here is the combined mass of the arrow and the target, and we're looking for our velocity of them both afterwards. So we can solve for v2 to give 0.02 meters per second.